All right, welcome back. So we'll look into chapter 12 today. More details about the source of magnetic field. So in the previous chapter, we talked about the electric current produces magnetic field. Okay, so um, electric current actually is caused by the movement of charges. So then if you look at the individual charges, the movement of individual charge actually will create a magnetic field individually, and then collectively for all the charges that cause the current, then it produces a collective magnetic field in that sense. So the magnetic field produced by an individual charge that's moving with the velocity of v here, um, at distance r away from the charge, the B field is equal to, according to this equation, so mu naught divided by 4 pi times q, that's the charge of the charged particle, times v, the velocity cross product of the unit vector r, which is in this direction here from the source charge to where your interest of your point is, divided by r squared will be the distance from the point of interest to your source, okay? Where this mu naught is the constant equal to 4 pi times 10 to the minus 7 in Tesla times meters over amps, okay, amperes. So that's the magnetic field produced by a charged particle. So in this case, the magnetic field is in this circular direction. So at any direction, that will be the tangential of that point of the circle, okay, of that curvature in that sense. So then the direction of the magnetic field, in this case, we can use right-hand rule. So the rule here is called, again, the right-hand rule, another version of it. So your thumb points in the direction of the of the current, which is the same direction as the positive charge's velocity. And your forefingers curve in the direction of the magnetic field. Okay, so in that sense, so at any different locations, you'll see the magnetic fields are in the circular patterns, okay, in that sense. So this then brings up the Biot-Savart law, which if you have a current inside a particular wire, now not necessarily have to be a straight wire, it could be a curved wire in general. So the current inside is, as we know, is defined as the derivative charge over time t dt. So then dq is equal to I dt. Okay, so if you take dq in the place of the equation earlier, a couple slides back here, so then this becomes dq. Then the magnetic field becomes derivative of magnetic field. Okay, so dB then equals dqv cross r. Okay, so then coming back here, dq then becomes I times dt. So q dq times v is then I dt times v. Okay, so I dt times v, v times dt then becomes dl, the distance travel, right? So because distance travel equals to velocity times time t, derivative of t. So then it gives you dl. So then this becomes dl. So then dB is equal to then mu naught over 4 pi I dl cross r over r squared. So this is called Biot-Savart law. So for the magnitude, so because this is a vector, it has direction. So cross product two vectors gives you a direction. The magnitude wise, then it will be just dB for the magnitude equal to mu naught over 4 pi I dl sine theta over r squared. Okay, so that will give you the magnetic field produced by this small section of the wire dl that at the distance r away. Okay, so that's the magnetic field. So if you want to look for the total B field, then you integrate through the whole wire to get that. All right. So first example here. So you have a current loop like this. So current goes in this direction and then comes back here. So it's asking you what's the magnetic field at this point of interest. Okay, so we can kind of analyze this. So this is the center of this curvature. So then we can divide this loop into 4 sections. So this section, this small semicircle, and then this straight, and then the other straight section, and then the larger outer semicircle. And then we can analyze, we can apply Biot-Savart's law to calculate what the magnetic field at this center point by each of those four sections and then add them up, okay, to be the total magnetic field at this P. Okay, so let's take a look. All right. So the problem stated, so let me sketch this first. So there's small semicircle, larger semicircle. The current goes in that direction for the 4 sections. Okay, so this guy here for this section, right? And we can do the dashed line there. So we know that this, if you connect these two parts, it should go through this guy. So this is I, and this is A for the radius, and then B. Okay. All right. So for this straight wire, okay, it will actually, if you extend, it will go through that. So then the distance from this guy perpendicular to the wire is going to be 0. Okay, or actually this guy goes through that. Okay, so in that case, or if you look at the small dl at this portion over here, right? And then this is the direction of r. Okay, so dB equals mu naught over 4 pi according to Biot-Savart's law, I dl cross r unit vector over r squared. So this will be also the direction of a unit vector, and then these two are in the same direction. So the two vectors, this vector and this vector, that's in the same direction. So the same directional vector cross product each other will be equal to 0 because the magnitude will be dl times r times sine of theta. Okay, so then contribution from this part of the loop to the magnetic field at this point will be 0. The same here will be applied to this part, okay, because this is the direction of r, right? R or r hat, the same direction. And then this is dl somewhere here. So they are in opposite directions. The angle is 180. So sine of 180 will be also 0. So dl times r times sine of 180 should be also 0. So 0 contribution by this part and then 0 contribution by that part. So the contribution should be coming from just this semicircle and that semicircle. Okay. So we'll call contribution by this semicircle as B1. So you can do B1. All right. And that should be coming from integration of dB1, right? From one end to the other end, okay? And then, so let's imagine we have a small portion over here, which we call as dl, okay? So then in that direction, tangential direction, okay? And then this will be the r direction or r hat direction. So these two should be having an angle of 90 degrees, okay? The magnetic field by this guy at that point, so we can apply right-hand rule. So your thumb goes in that direction, okay, direction of current, and 4 fingers curve in the direction of that. So the direction of the B field actually coming out of the paper, okay, by this guy, all right? Now by this one, so let's set this up. So this is the outer paper being X, and then Y horizontal, and then Z to be the vertical direction, okay? So then by this one, it goes out of paper, so that's positive X direction, okay? So we can say, okay, so then if we do that, then this is integration of mu naught over 4 pi I dl cross R for R square, okay? So this will become integration of mu naught over 4 pi I is the current inside there, and then dl, right, times R will be 1, over r would be this guy, a square, okay, in the I direction, just in I direction, okay. So it looks to us that this is the variable, the L, dl, okay. So I is not dependent on that. I is not dependent on it. So everything is not, else is not dependent on that. So this would be mu naught I over 4 pi a square. And then just integration of dl in I direction. Okay, so integration of dl in for the semicircle, right, it's the arc length that gives you arc length. So pi times a. For full circle is 2 pi a. So for that, then will be pi times a. So this will be mu naught I over 4 pi a squared times pi a in I direction. Okay, so pi and pi would cancel, a and then this a would cancel. So this gives you, okay, so then by B1, it's going to be mu naught I over 4a in the I direction, okay? Now for the outer semicircle, okay, so we're going to take again, but this small dl over here, it could be anywhere, so it doesn't really matter, okay? So this dl is in this direction, and then this is the r direction. So again, that's 90 degree. So B2, we call it B2 then. B2 equals integration of dB2, okay? And integration of mu naught over 4 pi times I, dl in this case cross r, that over r square, okay? So again, dl and this guy are in the perpendicular direction, so it'll be 90. So this will be just mu naught I over 4 pi times dl, and then that will be 1, okay? Divided by, in this case, now b squared. Now the r becomes b, and then so we are this time we are in that direction, or thumb is in that direction, okay, and then four fingers curl. So it now goes into the paper for B2. Okay, so that means it's minus I direction. Okay, and you'll integrate. Okay, so the same as that. So the result will be similar to this guy, but now you change A into B, and then with minus I, so it will be minus mu naught I over 4B times I direction. Okay. So then you add these two up, B1 plus B2 to be the total B. Total B equals to B1 plus B2. Okay, so this guy plus that guy. So mu naught I over 4A in the I direction minus mu naught I over 4B in the I direction. Okay, so that tells you this is mu naught I over 4 of 1 over A minus 1 over B in the positive I direction. Okay, so that will be your final result. Okay. All right. So let's go back to the slide. All right. So now let's take a look on a simple example when you have your wire just as a straight line. Okay. So if the wire is a straight line, then you again, in this case, you take a small dx, that will be dl, okay, but let's just use dx. So if this is the total wire, current is I, we take this small one, and then let's say in the middle somewhere here, that's your origin. So if you have a straight wire like this, and then you then will be looking at the magnetic field by this point P of your interest, then integrate through, okay? So mu naught I dl and then r, and then the angle is theta, okay? So you integrate through. So mu naught I dl cross r hat over r square. So then that will be r, okay? So it will become I sine theta dx, that's dl, and then over r square, and then integrate through the wire. Okay, now r should be, this is the integration variable x, okay, and then derivative of x. So r is a function of x, in this case, so x squared plus r squared, okay, capital R squared. Sine of theta is also a function of x, okay, so you can see that. Opposite divided by hypotenuse of this small r, which is this guy. So then you integrate. So if this is infinity long wire, Okay, so you integrate from minus infinity to positive infinity actually of this whole wire. So everything in the integration is squared for the x is squared. So then that means it doesn't matter. It's symmetric from minus infinity to 0 compared to from 0 to infinity. Okay, so then you get twice actually of the integration, twice our integration just from 0 to infinity. Okay, so substitution of everything, these two into the first equation, you get that. And then you integrate from minus infinity to positive infinity, but that means the twice of from just 0 to infinity. So then twice of that makes the 4 down here becomes 2. Okay. All right. So then this will be what you have. Now integration of this gives you the result of this guy. All right. And then in from 0, lower limit, upper limit being epsilon. So plug in those into the parentheses or the integration result you get at the end, this guy. Okay. All right. Because the upper limit goes in here, right? It becomes infinity, and then if this is infinity, this guy is small. So then that just becomes infinity over infinity, which is 1, which is this guy. The lower limit comes in, becomes 0 here. So then everything is 0. So this is your result. So magnetic field by a thin straight wire then becomes mu naught I over 2 pi divided by r. R will be that distance. Okay. Okay, so then let's take a look on this example here. It says you have a long straight horizontal wire carries a left to right current of 20 amps. If the wire is placed in a uniform magnetic field of magnitude of 4.0 times 10 to the minus 5 Tesla, that is directed vertically downward, and it's asking what's the resultant magnitude of the magnetic field 20 centimeters above the wire, and also 20 centimeters below the wire. Okay. So let's start with sketching the problem here. Switch my camera. All right. Okay. So this straight wire, it goes horizontally, that carries current. Okay. It says long wire, so you can imagine this is an infinitely long wire. Okay. With current inside it, 20 amps. Okay, so current inside this guy is 20 amps. I equal to 20 amp, 20 amperes. All right. So it says there's magnetic field straight vertically downward. Okay, so that's magnetic field. Downward, 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 and then this is B. Let's call it B0. External B field, 4.0 times 10 to the minus 5. Okay, again, let's do X, Y, and Z like that. So I, J, and K, or you want, if you want, you can call it X, Y, and Z. So X will be perpendicular to the paper, J will be horizontal, and then K will be vertical. Okay. All right, so it says 20 centimeters above. So if this is 20 above, this will be distance R, and then also 20 centimeters below 20 centimeters, both and 20 centimeters. So external magnetic field, and then induced or not induced, the magnetic field caused by this wire. So right hand rule, direction, so it curves like that. So that means above this guy, it's coming out of the paper. So that will be dot. Okay. For the B field produced by that guy, let's call it B1. On this guy, it's going into the paper. This is also B1. Okay. They are same equal distance, so they should have the same magnitude, but just opposite directions, right? So let's calculate what would be the B field, B1, the magnitude. B1 is equal to mu naught I over 2 pi r. The result we got from the previous slide, okay? So you can go one slide up. The magnetic field produced by a infinitely long wire, okay, at distance r away is equal to that. So you can plug in the numbers. 4 pi times 10 to the minus 7, everything in SI unit, and then 20 amps, okay, divided by 2 pi times 20 centimeters, that means 0.2. Okay, so that gives you 2.0 times 10 to the minus 5 Tesla. Okay, so when you are at this location, let's call it A, 20 centimeter above, your total B field then will be B0 plus B1. Okay, so B0 is minus in the minus direction, right? So minus, that is 4.0 times 10 to the minus 5 Tesla in the minus K direction. And then plus B1 will be 2.0 times 10 to the minus 5 Tesla in this case, out of paper, so positive X direction, okay? All right. So these are the components, the X component and Z component, there's no Y component. So then B will be equal to square root of the X component plus Y component, which is 0 plus Z component square, okay? This guy is 0. So 2.0 times 10 to the minus 5 square plus 4.0 times 10 to the minus 5 squared, and then square root. That gives you 4.47 times 10 to the minus 5 Tesla, okay? Now, the magnitude will be the same for part B because for part B on the second one, 20 centimeters below, it will be having the same magnitude because it will simply, this guy will become minus. The direction becomes minus, but you'll still be doing square root of S component and Z component square. So minus being squared, then it will be the same, okay? So it will be the same. Magnitude of magnetic field will be the same as the 20 centimeters above. Okay, so the same as that guy. All right, so now let's go back. So if you have one wire carries current, right? It produces magnetic field. Now, if you have a next wire, a second wire next to it, then there will be interaction between the two. Okay, so imagine for this one being the first one, so you produce the magnetic field in the blue circles, circular curves, right? And then the second one now will be in the present of that field produced by the first one. So then F2 on the second wire, it will experience force F2 will be I LB, right? B will be produced by the first one. Now B1 is equal to mu naught I over 2 pi r, okay? So if the separation is r, now in this case, small r instead of capital R. So then combine these two together, mu naught I 1 over 2 pi r in the place of B1, then you get the result of this guy, mu naught I 1 I2, and then divide by 2 pi r times L, but you can move L to the other side, so F divided by L, okay? So that means force per unit length, okay? So then equal to that guy, okay? So this is the, you calculate B1 first and then use ILB for the force, okay? On this guy. So I is in this direction and then this guy is in that direction, okay? So use your right hand rule for the B field produced by the first wire at location of second wire. So that's going into the paper. Now use the second right-hand rule. You can determine the direction of the magnetic force. So in that case, you line your four fingers in the direction of the, or in this case, let me see. Yeah, so the thumb goes in the direction of the current, and then the forefinger goes in the direction of the B field, which is inward. So the palm faces into the direction of the force. So F is equal to that guy. So you can see force is towards the first current. Okay, so this is a top view. So for the two current carrying wires, if the direction of currents are parallel to each other and in the same direction, so the force then will be attractive force. If you flip one of the current in the other direction, then the force will become repulsive. Okay, so the same direction for the current, repulsive force, opposite, and becomes repulsive. Okay, all right, so let's take a look on this guy. It says you have two long straight wires are parallel and 10 centimeters apart. One carries current of 2.0 and the other carries a current of 5.0. If the two currents flows in opposite direction, what's the magnitude and direction of force per unit length on the wire? And what's the magnitude and direction of the force per unit wire if the current are in the same direction? So I think the magnitude will be the same. Okay, so because you use the same equation, but the direction for the force will be opposite. Okay, so if the currents are in the opposite direction, we will get repulsive force. Okay, so on this one, we know that the force will be repulsive, and force over length is mu naught I1 I2 over 2 pi r. Okay, so we can calculate that. So this will give you force per unit length F over L. Okay, so 4 pi times 10 to the minus 7, or in SI unit, 2 times 5 divided by 2 pi times 10 centimeter, which is 0.1 meters. Okay, so this will give you 2.0 times 10 to the minus 5 newtons per meter. Okay, because this will be force per unit length. Now on the other one, it will be just attractive force if they are the two currents are in the flow in the same direction. Okay, with the same magnitude. Of that one. Okay. All right. So let's move on to next one. Looking at what if you have a special case of the circular loop that carries current. Okay, so in this case, you take a small dl, all right, and then this is r. So these two are perpendicular to each other. Okay, so then the magnitude for the B field at the center of the loop, okay, it's coming out of in this direction. You can use your right hand rule again. Your thumb in the direction of the current on the top there, and then so it curves in there. And then you can circle it around, so it's always pointing in the positive z direction in the figure shows there. The angle theta will be 90 degrees, so this guy becomes 1. Okay, so then dB will be just equal to mu naught I dl over 4 pi over r squared. Okay, and then you integrate to find the total B field at the center here. So I is not dependent of dl, r is not, they are both constants. So then just integration of the whole circle, that means the closed path, okay, dl. So that will be the circumference of this circle. So 2 pi r for the result. 2 pi and 4 pi cancel partially, and then r cancels the square. So you have 2r at the bottom here, you have mu naught I at the top. Okay, so the total B field will be equal to mu naught I over 2r. So this is looks similar to the magnetic field produced by a current carrying wire, which you have mu naught I divided by 2 pi r. Okay, in this case, you don't have the pi. Okay, because the integration get rid of that. All right, So then mu naught I over 2R. All right, looking at this example, when the current, it says when the current through a circular loop is 6, the magnetic field at the center is 2. So what's the radius? Okay, so then this will be just apply the equation. This guy, you're looking for radius. Okay, so giving current, giving that, looking for that. All right, so it should be a straightforward one. So you would set up B equals mu naught I over 2R. So then R equals to mu naught I over 2B. Okay, 4 pi 10 to the minus 7. This is 2.0 times or 6, 6.0, 6 amperes divided by 2 times 2.0 times 10 to the minus 4 Tesla. Okay. All right. So you get 6 pi times 10 to the minus 3 meters or 0.019 meters. Okay. On that one. All right. Okay. So now what if you have your point of interest is not at the center of the loop, you are somewhere here. Okay, so the same thing, you'll take a small DL at the top here. Now thumb in the direction of that, and then your four fingers curve in the direction of the B field. So you'll figure that the magnetic field by that small portion of the loop will be in this direction. Okay. Now this magnetic field can be resolved into the Z component and the Y component. Similarly, you can find another portion down here, DL, symmetric to that guy to the center. Then the B field will be actually going in this direction, okay? And then it will have a Y component and Z component. So the Y component will actually cancel out. So the total B field will just have a Z component, okay? So in that case. All right, so for the Z component, so if this angle is theta, then this angle is theta, so then it will be sine of theta for the Z component, which is this guy, also this guy, again, the same thing. So we're doing mu naught I dl sine of theta over r squared, and then you integrate through the whole circle for the total. I is independent of dl, and then r is also independent of dl, okay, because r is this guy, which is a fixed number if this p is fixed location. So sine of theta then is also not dependent of dl, so then integration will be just the integration of through the whole circle, okay, the closed path. All right, so it becomes 2 pi r. And this will be then the result, okay? So mu naught I sine theta over 4 pi r squared, 2 pi r. And small r, you can write because small r is square root of r squared plus z squared. So r squared plus z squared and square root, okay? The 2 pi and 2 pi you cancel, so it becomes just 2, okay? And then there will be r squared. Sine of theta gives you another square root of r squared plus z squared. So at the end, you have 3 halves, okay? At the bottom, on the top, you have r squared, okay? One r comes from this guy, the other one comes from the sine of theta, all right? So if z goes to 0 again, that means z is that point, okay? So then this then reduces to back to what we had before. So then it will be r to the q at the bottom here, then will be similar to this result, okay? All right. So we have looked at two wires close to each other. Now, what if you have the two loops? Okay, so like one loop, okay, and then so for one loop you actually get the magnetic field. You can use your right hand rule, right? So if you know the direction of the current, so then it gives using this. Now, if you have a second loop, okay, or in this case, so the magnetic field is produced in this fashion. And that's similar to a bar magnetic field, okay? The magnetic field produced by a bar magnetic field. So a current loop, like this circular loop, a result of the magnetic field is same as a bar magnetic, okay? And if you have two loops close to each other, if they carry the current in the same direction, like clockwise, or otherwise in the opposite direction as figure B shows here. So these two then, if they are in the same direction, the result, this is a bar magnetic field of this first one, and then this will be the second one. So you'll see that they actually have south pole to the north pole, so they will attract each other. So if they are in the same direction, the currents in the loops are in the same direction, they will attract each other. If otherwise opposite direction, they will repel each other. Okay, so we'll stop here for today, and then coming back next time for the remainder of this chapter. So I will see you guys next time. Bye.